morning, good afternoon, good evening. In our area, Germany, we have currently 30 degrees Celsius, which I think is roughly 86 degrees Fahrenheit. Let me introduce the speakers of the session today. We are talking for 1 hour about the integration of the TSN of 5G with time-sensitive networks. My name, as I said, is Uwe Rüdenklau. I'm the moderator coming from Infineon and also the vice chair of the working group 4, which is related to liaisons. This is today live from Munich. So let's welcome the speakers of today's webinar. Here we talk about 5G and time-sensitive networking, TSN, and the technologies related to this for future industrial communication technologies. And we look into this, how this can converge from communication area for a wide range of services as well as network infrastructure, and how this can be 5G can be applied to the industrial networks together with TSN and 5G. What is needed? So our first speaker who will talk today is Dr. Dietmar Bruckner from BNR ABB, and he is live from Salzburg. So we are getting already a little bit international. The next one is Mr. Lukas Wüstenau from Hirschmann Belden company. He's live from Stuttgart. Okay. And last but not least, Dr. Kun Wang from Ericsson. He is live from Stockholm. So you see, we are from 4 different locations having this live seminar. And with this, I would hand over to our first speaker. Warm welcome to Dietmar to talk about the details.
Very good. So also from my side, hello everybody, good morning, good evening, good afternoon, from wherever you attend this web meeting. My name is Dietmar Bruckner from B&R. Short words about B&R. We are a system supplier for automation components in industrial automation, mainly for machine customers. And TSN for us is a very important topic and will constitute the communication backbone for industrial communication of the future. And that's why we are very active in standardization of TSN and particular of OPC-UA over TSN and also in communication with 5G. And the topic of today will be presenting how TSN and 5G can be integrated for industrial use cases to have wired and also mobile applications to give them deterministic communication infrastructure for exchanging their process data. The topic of today's call is covered in a white paper from the 5G-ACIA. And so if that works. Going to the next slide. So what you see here is a screenshot of the table of content of this white paper. And basically the talk today will follow the content of this white paper. So I will start introducing some main capabilities and features of TSN. Then I will hand over to Lukas, who is going to talk about industrial use cases for TSN and also some bridge capabilities for TSN and 5G. And then Kun will dive deeper into the integration and validation of 5G TSN combined networks. You can also, the white paper is for free, so you easily find it in the internet and can download also this white paper. Before we are going to start with the actual content of the presentation, I would like to start with the first poll. So you see the question here. This is very basic information about the audience today. So we would like to know which stakeholder group are you belonging to, and the options for you are information communication technology or operations technology, academia, or others. I just see the result of the first poll. Since it's on my screen, probably you also see it. So we have almost 40% stakeholders from ICT, 20% OT, 25% academia, and 12% others. Very good distribution among stakeholder groups. And now the second poll has opened about the regions. So Salzburg, for those who don't know, is in the very center of Austria. So for me, it's Europe. And here it is, yeah, 80% Europe. So quite Europe-centric, the participation of this poll today. We have also 12% Asia, 5% North America, and 1% South America. Hi guys, South America, quite far away, different time zone. I very much appreciate that you are also going to attend this webinar today. Thank you. Okay, now what's the motivation for TSN as such in a factory or in factory automation? Most of you are probably very much aware of this picture that we have here to the left from the automation pyramid. This is the way how most industrial automation and industrial communication systems are organized today. We have this usual layers in the automation pyramid. On the bottom, we have the field I/O, then we have the controllers, and then we have the planning, the production planning systems. And very often today, the different machines, they have different communication systems, sometimes based on some serial field bus. Today, also many based on different industrial automation, industrial Ethernet technologies. One of the problems with these technologies is that the modeling of the data that's being exchanged is very much technology dependent, and also the understanding of determinism in the different networks may be different. So coming to a harmonized, seamless exchange of data between the different existing systems is sometimes very tricky. And this is summarized here in this bullet list. So very often the situation is that the communication infrastructure in production environments is historically grown. So many of the machines and the plants, they have a long history where parts are upgraded. Other parts are still in their duration. So many different communication technologies exist within the same actually communication domain. And those are fragmented. The data cannot be exchanged directly, so it's non-interoperable. And also the communication infrastructure, so to say, starting from the physics and from the exchange of data, is also very often not interoperable, because the real-time industrial Ethernet technologies, they have, at least the hard real-time ones, they have proprietary implementations of the MAC layer of Ethernet. So in such a system, standard Ethernet devices cannot participate, and there is no direct exchange of data between different technologies and also standard Ethernet devices without gateways. And what's happening due to request of many end users and customers, and also due to request of actual vendors, device vendors and also machine vendors, is this translation, what you see here on the right side. The new concept is called the automation pillar. And the basic idea is that all the participants in the communication networks, they have equal access to the network. So this means that the communication networks in this automation pillar concept, they are potentially flat. Why potentially? Because still in a large factory, it makes sense to have segmented networks and to have different management of networks. But potentially the technology should be capable that all participants could access the same network. With respect to data that's exchanged on those networks, also there is a big move and a big push towards interoperability. Maybe you are aware of the field level communication initiative of the OPC Foundation, for instance, where OPC is currently making a big move into such networks for being the data modeling language that's exchanged in such industrial networks. Another thing is that since TSN TSN is a bunch of extensions to standard Ethernet, providing various methods and tools for bringing determinism into standard Ethernet networks. So the communication infrastructure is based on open standards, which also brings some benefits to the user base, because there is plenty of different vendors that can, on an equal base, can participate in such networks, in such a network. And last but not least, the topic of individual or proprietary interpretation of real time. This is something I will come to also in a couple of slides. With TSN networks, since there is standardization on the real-time options and real-time guarantees such a network can bring, this also means that the idea on how deterministic isochronous traffic can be, how deterministic cyclic traffic can be, how deterministic event-based traffic can be, there will be specification around that. So for sharing a universal understanding of real-time capabilities of TSN networks, which is also new. This didn't exist before in industrial Ethernet. So now making the match with 5G, what you see here on the right side, I will start with the right side. The TSN side is basically TSN standards. They are developed in four distinct areas. The one is the actual traffic shaping mechanisms. So those are the mechanisms, how the network behaves and how the different packets on the network are treated in order to have these timing guarantees or determinism guarantees. And then there are standards around time synchronization. This is also explicitly because time synchronization is the backbone for most of these traffic shaping mechanisms. Then there are standards around reliability, so that you can specify or configure different paths for the same packets or for the same streams, to have some seamless kind of redundancy if some communication routes have problems. And finally, there are standards around resource management, so how to configure the network, how to establish streams, how to also decommission different participants of the network. And what's all about is guaranteed bounded latency for different types of streams or different types of packets on the network. And if we match this now to the left side, also in 5G, there are specifications or parts of the specification around the same topics. So there is something about time synchronization, there is something about low latency communication, resource management and reliability. So this is actually a perfect match between 5G networks and TSN networks. And this perfect match allows for a user of those technologies to have actually the picture of one network. So the management and the configuration can be harmonized, and also the determinism guarantees can be extended over the boundaries of wired and wireless networks. And this is something that happens currently in standardization and will be also dived deeper into the course of this webinar. So obviously, what are the benefits of extending TSN capabilities into the wireless world? So it's being able to integrate moving components like AGVs, automated guided vehicles, mobile robots, then also saving on cabling and deployment cost. And another thing is 5G currently represents the only wireless standard that goes in this direction, in this close relationship between specifications with the wired world. And yeah, it's stated here, both integrated can be integrated into a common communication infrastructure. As promised a bit earlier, this slide deals a bit with the so-called traffic types, or with the different types of guarantees on the network. I don't want to go into a lot of details here. The message of this slide is in the past years, in various standardization activities, we had discussions about what are the actual requirements to a network for different types of traffic. And this discussion resulted in the specification of traffic types. So for instance, this isochronous for hard real-time traffic. Then we also have cyclic types for softer type of real-time events and so on. We have then the requirements to the network, and for TSN networks, we have a mapping to the various TSN traffic shapers. So here you can see a list. I don't want to go through all of them. If you are interested in more details, please refer to the white paper. What I'm going to do in the following 2 slides is put a highlight on 2 of the most important TSN features that we need for implementing determinism on TSN networks. The first of them is obviously time synchronization. This is standardized in this standard here. It's IEEE 802.1 AS, and the latest revision dates back to last year, 2020. And basically, what AS describes is that there is one time master, or it's called grandmaster clock in a network, and this grandmaster clock distributes the grandmaster clock value among all the slaves. And additionally, the propagation delay, so how long it takes for distributing this time value, it's compensated. And this compensation happens locally on every device. So every device measures for itself when does the frame get in and when does the next frame get out. And this delay will then be also communicated to the next communication partner. And this way, if there is hardware support for this timestamping in wired networks, there can be achieved a precision of 1 microsecond, and the precision it's stated here is the difference between the grandmaster clock on the grandmaster and the local clock on the slave. So the slave clock is within this 1 microsecond range compared to the grandmaster clock running on the grandmaster device. Yeah, there are a few options on how to operate such a .1 AS network, but there is no point for today going into this in detail. The second standard that I would like to introduce here is so-called scheduled traffic, which is specified in IEEE 802.1 QBV. And scheduled traffic deals with the definition of time-aware gates for queues. What you see here is 1 egress port. So at the bottom here, the frames will exit or egress a switch. And most of the switches have up to 8 traffic queues that they manage, and where they have various strategies on which queue will be emptied first if there are frames in multiple queues. What the scheduled traffic additionally adds to this system is time-aware gates. So you have this gate control list here. This is a cyclic list with a cycle time, for instance, 1 millisecond or 10 milliseconds. And then you can say for each point in time, which gates out of those 8 are opened and which are closed. And with this rather simple and elegant mechanism, you can reduce or even avoid inter-traffic interference between the frames. So for instance, if you want to have very high determinism, for instance, for the highest priority traffic class, then you can define time windows where only this queue has exclusive access to the network, and all the other traffic in the lower priority queues has to wait. And this way there is no interference from the lower priority traffic to this isochronous traffic. Just a note, QBV, it's a switch mechanism. If this is extended by time trigger send capability of the end stations, then also intra-class interference within one traffic class or one traffic queue can be minimized. So if the sending times and the forwarding times of the frames are known, then a schedule can apply it where really individual frames can be transferred through an entire network without interference with any other frame. And this is actually for the applications with the highest requirements to performance. This is what's been done in industrial automation. Okay, with that, that was a short introduction for 2 of the most important TSN mechanisms. And I would like to close my part with another two polls. And the first one, but those two polls concentrate on the use of TSN. And the first question is, how important do you consider TSN for the factory of the future? And you have 5 options to click now, from extremely important to not important at all. So please cast your votes now. So here it is. And I see there is a large majority, 61%, who considers TSN as extremely important, and another 27% that consider TSN somewhat important for the factory of the future. We have nobody who says that it's not important or not important at all. Okay, this brings me to the last question of my part, which is, when will you actually expect that the more widespread adoption of TSN in manufacturing will start? And again, we have several options to choose from, which are some concrete years. So starting with this year until 2025 or 2026 and beyond. Or you can also click never, or if you don't know. So please cast your votes. There is 6% for next year, then there are 37% for 2023, and then there is some rather equal share of 2024, 25, 26 and beyond, and 15% who didn't want to specify some exact year. And yeah, as I said, we see that it's picking up to speed for the first interested customers. The expectation is that next year and also 2023, really large numbers of customers, or maybe in 2023 also majority of users for new designs for controller-to-controller communication. They are going to introduce standard Ethernet networks with deterministic capabilities, so which is basically TSN networks. With this, I would like to hand over to Lucas.
While the screen sharing starts, I'll firstly quickly introduce myself. My name is Lucas Wüstener. I'm from Hirschmann, Belgium. Hirschmann is an infrastructure vendor supplying switches and bridges for industrial networks, also focusing on wired and wireless technology, so also 5G. And therefore now I'll focus a little more on the complete network side of this whole topic, give a short introduction on how typical scenarios in complete networks look like, how it all can be combined as a network administrator view, and then hand over to the specifics of the 5G details to Kuhn afterwards. So let's then first start with TSN industrial scenarios that we have, and also Dietmar already slightly mentioned within his slides. We'll first start by analyzing the example topology that we have here. As Dietmar said, usually industrial networks are very hierarchical. This has different reasons. One major reason is security. Another major reason is that in the past we have seen very isolated machines. So we'll go through that now in detail. On top, we have some central rooms, some edge cloud, some very high-level backbone, maybe connecting multiple sites also. So that's basically our local cloud. Usually, industrial applications aren't that connected to applications in the internet. So a factory automation would have that locally or distributed across multiple sites. On top, we'll have a backbone. The backbone has the functionality of connectivity. It connects, on the one hand, the central room to what we'll now see in the second, the field network, but also connect different elements in the field network to get connectivity. And on the bottom, we have our machine cells, production line. So basically the area where the actual factory automation happens, where you have all the sensors, the actors, and typically in current networks, most of the controllers. In this example, you just see 3 different levels of the network, but this can be extended to many more, depending on how granular you want to create your segmentation and your hierarchy. But it already gives a very good explanation on how to structure industrial networks. What we then have is, in this example, we show the brownfield scenarios. So this means all the elements in the network where we have a lot of legacy Ethernet devices. And this also covers basically all the elements where we have existing field buses that are deterministic devices, but they are to a certain extent not TSN aware. But we already have some TSN bridges in future there to create the connectivity between these deterministic legacy devices and the new TSN infrastructure. And to enable this connectivity, as Dietmar mentioned, that we have this more flat hierarchy, that everything can be connected to our central cloud. Does not need to be, but can be. On the other hand, we have the so-called greenfield. Those are usually more modern devices, new factories that are built up. On this side, actually all devices that take part in the TSN communication will be TSN aware. They already implement the new standards that have been developed by the IEEE and others. On the left-hand side, the brownfield, they have similar mechanisms. So they are all compatible, but it's a little different and different aspects to cover. But as we now have just different locations in our network, we have different groups of devices that cover different aspects. We also have different communication relations that we need to cover and that we need to take care of in our examples. So we have 3 major use cases. The first one I want to start with, the controller-to-controller communication. You can see 2 examples here on this slide. On the left, you can see 2 controllers on the field network communicating with each other. This means that basically you have 2 different robots that work on the same piece, but on more far, not very close to each other, so they might not collide. Otherwise, you probably want 1 controller for that, but if they are a little farther away, but they still need to know what the other one is doing, such that the work piece isn't harmed, for example, or no people in the factory are harmed. And then we have, as a second example, in the cloud, some controllers that need to communicate. They also can have the same functionality of controlling elements, what we will see now. So the second communication relation that we need to cover with TSN is the controller to device. This is the actual control. So we read out sensors, we communicate to actors to tell, for example, some motor what to do. This can be either on distributed controllers, how we call the controllers on the field network. They are distributed across the whole factory and all have their small functionality. They control their own field devices. Or we have centralized controllers, which have multiple tasks and communicate to many different machine cells probably. And they are in our local cloud and communicate across very large communication relations through our backbone to the machine cell. So this is this flat hierarchy that we mentioned already, where we possibly have very large connectivity between field devices and some edge cloud. And as last example, we have this device to compute. This is now what you can, or what everybody's talking about with edge compute, where we have small clouds that really do cloud computing, usually also locally, but maybe also in the real cloud, in the internet, if it's not too time critical. But with TSN, we also need to cover this communication, because also this edge compute might be time critical. Right, so here you can see as a summary the 3 different communication relations that need to be covered by TSN. As Dietmar said, we have different mechanisms to achieve the different traffic types that exist, and the different traffic types basically define how tightly coupled the control to some end device is, and how high the requirements are for certain communication parameters. But you can see that at the end, the complete network needs to support TSN to a certain degree. What we've also talked about is time synchronization. Many of the standards, and mostly the QBV standard, this time scheduling, needs time synchronization, such that all devices that are part of this one communication behave synchronized and schedule their traffic synchronized. In this picture, I just want to cover it briefly. You can see different time domains. We have, for example, one working clock in the machine 1 and another working clock in machine 2. We have a larger time domain here, and you can already see that basically elements that should communicate with each other then also need to be synchronized to each other. But of course, we don't want the complete factory to work on the same time base. This has different reasons. For example, we are now more robust to failures if we split it up. So for example, if now here one device fails, which leads one grandmaster to have a completely wrong time and drift all the time, some other working clock domain is not influenced by this. And also, as Dietmar said, the precision is also very important. And he mentioned the 1 microsecond. This is the goal and also possible for quite a number of devices, but not if you have basically unlimited devices. As you need to communicate across multiple hops, the precision or the guarantees for the precision get weaker, and the more devices you include, the closer you get to this 1 microsecond, and therefore smaller domains might have more precision. So basically, to summarize, depending on the participation within the communication relations of TSN, a device might have different numbers of time domains to be synchronized to. Usually it's 1 or 2. This depends on 2 factors. We can have redundancy for the synchronization, or you can have gateway devices which communicate on different interfaces in different domains, and therefore need to behave differently depending on the domain. This is at the end, and we'll see that in Kun's slides again, important, because at the end, if we combine TSN domains within a 5G network, we need to come back to this requirement of 1 to 2 working clocks per domain again. But as you have seen now, we have many features, we have large networks, and at the end, somebody needs to administrate that. So it just doesn't come from itself. We have now introduced all the features, we have introduced how that needs to play together. But now we want to talk about how to configure this. Therefore, within 5G, and we'll see in a second how the TSN comes into the role with the 5G. It's defined that we focus in the first iteration on centralized configuration. Centralized configuration in terms of the IEEE means that we have a centralized network configuration, short the CNC, and we get the requirements of the streams from so-called CUCs via a defined protocol. There's currently the QCC protocol defined, and also another project covering exactly this topic. It's the QDJ project in the IEEE. All the other elements we'll quickly go over now in the following. So first, we have our end devices communicating with which precision they want to communicate. This basically is, again, the representation of the traffic classes that Dietmar presented. So we communicate how quickly we need to, or with which latency requirements we want to communicate through the network. Then this is transferred to the CNC. The CNC calculates a network configuration across all the bridges in the network. So it decides a path. It says, well, okay, now we need to reconfigure the following TSN features, and does that via IEEE network management protocol mechanism. So for example, netconf, restconf, or SNMP. Then we communicate back towards our user and application layer, which configuration we have chosen. And in step 5, the end devices get back their configuration on when they need to communicate with which addresses and all that stuff. And as Dietmar already said, 5G is very similar from the whole feature set that it provides to a TSN bridge. And therefore, this whole system will work in future, no matter if we have a real bridge or a 5G bridge. And we'll come now within the following slides to what that means to have a 5G bridge. Because until now, you know that 5G has a backbone and then many mobile clients. And probably you have not heard of a 5G bridge so far. So let's have a look at that. We have again our network. And within this network, we now introduce a 5G system, which is a very large block because it can cover large distances across your whole factory, across probably also many sites or halls in your factory. And we define that this complete system is now our TSN 5G bridge, which has a network side ports. Those are the fixed ones where we have our backbone connected to the TSN backbone to our cloud. And then we have many mobile ports, which are mobile robots and some AGVs that move around in your factory. And you can see now that the 5G link itself, so the 5G connection, is hidden within this 5G bridge. So basically what we can achieve with that is this complexity of the 5G system, because it covers the same types of mechanisms as the TSN bridge, but itself introduces, again, more complexity in configuration. This is all hidden and exposed to the network via the normal network management protocols, and can be administrated either by an administrator or a CNC CUC configuration entity while we are in operational mode. Additionally, what we can achieve with 5G is that we split our complete 5G system into virtual or multiple virtual bridges, and therefore also now this different time synchronization comes into place. So for example, we can have now small TSN 5G bridges per machine and connect them in a single manner, such that we have our small time domains again, or smaller TSN domains to isolate our communication. This has security, performance, and reliability reasons, if you like that. So now, as we have covered in a quick introduction, how this whole network topic plays together, how the 5G can be placed within that, we will quickly like to know how important you consider 5G in a factory for the future, because it adds more complexity, but also gives many performance benefits. And therefore now the next poll is opened. You can already see it. We have a few different answers, 5. And we would like you to rate how important you consider 5G for the future. Okay. Oh, that's very clear voting for very important. That shows basically the importance of our work and that we cover these topics that you can use that in future. As a next question then, similar to the questions before, would be how quickly do you expect 5G to be within manufacturing? So how do you see that we can have it in future? So you will have the same answers as for the TSN question. And basically, we would like to know if you see that we can achieve that already within the next years or that we still have many steps in front of us. Okay, so yeah, probably we can say that this is midterm, that first 5G applications come to our factories, which is very nice to see that you are confident for that. Perfect. Thank you very much for this. And now I'll hand over to Kuhn to cover the details.
Hi, my name is Wang from Ericsson. Thanks, Lucas and Dietmar, for the good introduction and the topic. So now I'm going to share with you about the 5G system capability and how 5G can interwork together with TSN. So first, as Lucas has mentioned before, the whole 5G network actually can be modeled as one or more TSN virtual bridges. So there are two types of translators. TSN translators are introduced for 5G system to interact with TSN network. One is at the control plane, that is the application function to interact with the industrial network control and management function like the CNC. And then the other type is on the user plane, which we have two places. One is on the fixed network side, that is on the user plane function of the 5G core network. We call it network side translator. And the other one is in the mobile device, that is called device side TSN translator. The industrial devices that can be connected to a mobile device actually can be, for example, a grandmaster clock for the time synchronization, or a programmable logic controller, a field devices, or even a bridge. The 5G virtual bridge provides the Ethernet and the TSN connectivity via the ports in the same way as the wired TSN bridge does. And the TSN communication is possible via any of the port pairs of the 5G bridge. In this slide, we take a closer look at how does 5G system handle the TSN traffic. The 5G can interact with the centralized network configuration via a standard interface based on the QCC defined. The 5G reports its capability to the CNC, for example, like bridge port management information, topology information, bridge delays between the ingress and egress ports. And then, as Lucas said, the CNC will use this information to calculate the path, the schedule, etc. Then after that, the 5G also receives the configuration from the CNC through the same control plane translator, TSN-AF. This information can include the, for example, traffic forwarding rules, QBV scheduling information, and the per stream filtering and policy information. This received CNC configuration is then being translated into 3GPP specific procedures. For example, in order to carry the TSN traffic inside of the 5G system, the 5G can set up different quality of service flows to carry TSN streams that with different cost requirement. Each of those quality of service flows need to be properly configured with parameters such as prioritization, latency, and reliability. The 5G system also defines the right filters at UE side and the UPF side. This is used to map the TSN traffic into different 5G course flows. In order to support the TSN time synchronization, 5G is implemented as a 802.1as compliant time-aware system. Due to the flexibility of the 5G system, the grandmaster time source actually and also the sync devices can be located anywhere inside the factory. The grandmaster time source can be connected through the existing wired network and fit into the 5G system, then wirelessly distributed to a device that is connected to a UE. On the other hand, the grandmaster itself also can be mobile. By attaching the grandmaster to a UE, then the timing information can be either distributed to an end station on the fixed network side or to an end station also connected to a mobile. The 5G system performance also ensures the high accuracy of the time synchronization service. It can support up to 128 GPTP time domains with error less than 900 nanoseconds. Dietmar and Lucas previously has introduced how this industry use case can be supported by wired TSN. And in this slide, we can see when 5G is introduced, how 5G and TSN can work together to support different use cases. On the left side, we can see the controller-to-controller application that can be supported by attaching a UE to the controller, and then the communication between the controllers becomes the UE-to-UE communication via the network. The UE attached to the PLC can also communicate with a fixed network where you have a controller connected. We can also see a possible redundancy solution, frame replication and elimination for reliability, 802.1cb can be implemented between this controller-to-controller communication by taking two disjoint passes, where inside of the 5G system that can be implemented by taking different UPF as different 5G bridges and different RAN nodes, and also two different radio interfaces. For the device to compute communication, the field devices can be attached to a 5G UE, and therefore it can direct transmit the data back to the servers in the edge cloud. On the right side, we can see the controller to the device use cases that can be achieved similarly by attaching a mobile terminal to the UE and also a mobile attached to a field device. If you have a soft PLC or centralized PLC, then the controller to device communication can be also implemented through the network. Here we come to a conclusion. We see the integration of 5G and TSN brings significant benefit for the industrial use cases. And 5G can provide good support for Ethernet TSN communication. And we see, based on the 3GPP release 16 and 17, that 5G standard support can already for all essential TSN features that are identified for the industrial communication. Meanwhile, we're also aware that TSN standards are evolving. We see the 5G standards also need to be aligned with the future evolution of the TSN. And thank you, and this concludes the presentation.
Thank you very much for the three presenters, and as I think we learned a lot on the details. As I said, all information is already asked. It's available also in the link which was sent. Interesting, as I said, is also for sure the feedback on the polls which you heard, where we got roughly 50% say that in 2023-4 TSN is important, and even up to 60% in the same time frame for the 5G. Yeah, we had already two questions which were directly answered. As we are tight in time, anyhow, we have two more questions from one person. I will read it, and then maybe you can, one of the speakers can answer. The first question, or even three. The first question is, what quality must 5G deliver for an optimal support of TSN? So what quality? It's a very generic question, but maybe a quick answer.
I think this really depends on the traffic types you want to support across your TSN network. You can see in the white paper more details about the different traffic types and their timing requirements. But if you think about motion applications, then you have very, very low cycle times below milliseconds. If you have process automation, you can have cycle times of up to multiple milliseconds. So it really depends then also on the clock synchronization and everything, what you want to combine.
Thank you very much, Lukas. Next question, I don't know if this is maybe for Kuhn. Does the 5G network exposure function play a role for TSN?
Yes, thanks. It was a good question. Actually, it plays a very important role here. So as we said, this interface interact with the TSN application function with CNC. Actually, that's the function that you have the exposure interface there. So all the 5G capabilities exposed through that interface to communicate with external CNC. So it is a very big role here, the network exposure.
Thank you very much, Kuhn. So we get more questions. Okay, so the participants are interested. So next one, I don't know, can answer this. Let's say, does OPC UA, where 5G-ACIA is in contact with, as the members know, can be used to communicate between devices at control room environment?
Yeah, maybe I take on this.
Thank you.
Actually, yes, this is very much possible. And there are already DCS systems, so distributed control systems, where the control system gets the information from the distributed controllers via OPC UA. And with the field level initiative and with devices that are also capable of communicating via OPC UA, also a communication across layers of the automation pyramid, as we have seen, is possible, so that directly the compute device can access the field devices. So that's one of the targeted use cases, actually.
Good. Thank you, Dietmar. The next one is for a person who joins 3GPP, maybe. What is the difference between the supported 5G TSN functions in release 15 and release 16? So the difference between the two releases. Somebody involved there?
Maybe I can take this one.
Thank you.
So actually, the major URLC features and the TSN support is only supported in the release 16. And the release 15 just have the, for example, the Ethernet PDO session and Mac learning, etc. So very basic Ethernet features, but the major URLC and the TSN functions integrations with 5G that are only from the release 16. And it's also enhanced in the release 17.
Yeah, thank you very much, Kuhn. And the last question, and then we come to the end. For larger 5G TSN network scenarios, I would assume, so the questioner assume that more than one CNC control domain, that there's more than one. So the question is now, which control mechanisms, protocols are considered to establish TSN streams running through multiple CNC control domains? So very dedicated question.
Yeah, I think this is a very good question, which also shows that we are not at the end of this whole journey. So the communication across multiple TSN domains, and therefore also probably having multiple CNCs being the masters of the single domains, isn't solved completely in the IEEE. There are different mechanisms discussed and also some prototypical solutions, but that's a very important question that will be answered within the next months and of standardization, and it covers the journey basically.
Yeah, thank you very much, Lukas, and also to again Dietmar Kuhn, and especially for the questions. With this, I would conclude this also without saying more, because I think it was very, very interesting, and we see from the questionnaires that was also an exchange between experts. So I'd like to thank for the participations. For sure, we are 5 minutes over time. With this, I want to just make a hint, besides thank you to the speakers, to the next webinar. So please join us again. This is on July 14th, similar time frame. As I said, everything will be also recorded for other regions. And that time we are talking about using digital twins to integrate 5G into production networks, where I think digital twins is a very important topic, hot topic also in many areas. And here we see this from our experts from 5G-ACIA, from Joseph Eichinger from Huawei, and Bernd Kircher from Festo. And we will proceed even further with this webinar series with an exception in August. So please join again on July. The registration is open, it's for free. And thank you very much again for the speakers for your great contribution. And everybody, see you again next time. Thank you.
Thank you. Have a nice day.
Thank you. Bye-bye.
Bye, thank you.
Thank you.